Hello, hello, hello. Feel free to ask any questions if you have any, Sean. By the way, can you hear me? You can chat it back. You don't have to actually speak if you don't feel like turning your microphone on.
Oh no, I hear you. It's all good.
Good deal.
And
Okay, thanks. Yeah, your voice sounds a
and
lot
I
better
think
too.
I think I have a question, but I'm not too sure right at the moment. I'll ask you in a
Okay,
little bit.
no problem.
All right, thank you.
See you. I'll be here. Let me see. 241. Got more people now. Feel free to ask me questions if you have any, everybody. I'm just prepping, doing my normal stuff, you know. All right, got some more people. All right. Okay, it's about time for class to start, everyone. Actually, it is past time. Anybody have any questions before we get started? And hopefully everybody can hear me. I've already tested a little bit.
Yeah, we can hear you this time.
Gotcha. Sounds good. I bought another microphone, but I can't find it. But I did find my old microphone, so now I've got it. I have no idea. I literally just bought it. Oh, there it is. I found it. Okay, cool. So, all right. So last time we were talking about energy. So I thought I didn't think I came off very clearly on that. So I thought I'd go ahead and start off talking about it. So we had worked out the simple harmonic oscillator, and the thing that you need to know more than anything is if you ever see a differential equation like this, and I'm going to write it in a general term. Let's say A.
Not sharing your screen.
X. Yeah, thank you. Nice catch. Of course, it was probably pretty obvious for you, but still. So yeah, let me do this. So here I got it. Okay. So there's a form for the simple harmonic oscillator, and the simple harmonic oscillator basically is when you have a mass on a spring, and the spring is essentially massless. So the force that it's subjected to is negative kx. And then the left-hand side of Newton's law is m times d2x over dt squared. Well, if you have a, some constant times dx dt plus b times x is equal to 0, then that is a simple harmonic oscillator. What we normally do, though, and I'm going to show it with the actual normal variables instead of a, b, and c. What we normally do, though, is we have d2x over dt squared plus, in this case, you'd see this becomes k over m x is equal to 0. So basically the rule is if you see a second order derivative plus a constant times a 0th derivative, in other words, the function itself equals a 0, then you know it's a simple harmonic oscillator. And that means the solution is x is equal to a cosine omega t plus phi. And that gives you essentially 3 variables here. You got a, you got omega, and you got phi. But it turns out that omega has to be the square root of k over m. What you're going to see with this chapter is there's other ways to get a simple harmonic oscillator differential equation, and the constants are not necessarily k and m. So you've got to be able to pick that out as when you get the leading coefficient to be 1, whatever the coefficient of the x is, the square root of that's going to be the omega. So that's probably the most important thing you get from this chapter, because this will appear over and over and over again in so many different ways. You'll see it as a RC circuit. So when you have a resistor and a capacitor in a circuit, you can get an equation like this. When you have a resistor and an inductor in a circuit, you can get an equation like this. When you have an atom near its equilibrium position near another atom, or an atom near its equilibrium position within a molecule, all of this stuff still holds. So what we did was for the harmonic oscillator, and we know that the harmonic oscillator, so back to energy for the simple harmonic oscillator. So for that, what we know is the energy is always going to be equal to the kinetic energy plus the potential energy. And the kinetic energy is 1/2 mv squared at any point in time. So that would be v as a function of t, for instance. And the potential energy is 1/2 kx squared, where x is a function of t. You can see that x is that function up there. And you can also see that v, which is dx dt, is equal to negative omega a sine omega t plus phi. So you can see that this little quantity out here is actually V max. Okay. So with that in mind, you can think of as a typical example of a simple harmonic oscillator, though we haven't covered it yet, I'm getting ready to do that next, is a kid on a swing. So a kid on a swing will swing back and forth, back and forth. In order for us to really make that truly a simple harmonic oscillator, we try to limit our angle that the swing is pulled back to a smaller angle, so that the sine of theta is approximately equal to theta. And it turns out if you do that, it's literally only about 4.5% error, even when you get to an angle of like 30 degrees. So it's not that big of a limit. But either way, if you think about that as your model, you know that when you're swinging on a swing set, you swing back and forth, back and forth. And when you swing to the top, all of your energy, because you've come to a stop now, and in fact, the top is the definition of your slowing down, slowing down, slowing down, boom, come to a stop. And if you wait a split second, you're going to be going back down. So you're definitely sitting still there. So there's no kinetic energy, but you actually have a maximum of amplitude, which in this case, we're going to call X max, which is A. So we can also say the total energy is equal to 1/2 K A squared. So that's one case where you get the total energy is 1/2 mv squared plus 1/2 kx squared is equal to 1/2 ka squared. But as you can tell, you could also say, well, 1/2 mv squared plus 1/2 kx squared. If you consider that kid again on the swing set, if you imagine him at his highest point, like we did here, he had no velocity. So all the energy was potential. But then the force, which is definitely a maximum right there, and continues to speed him up, 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 speed him up. In fact, the force only stops acting for a split second when the kid is at the very bottom of the swing. At that point, there's no force on him, but there's been constantly the whole time before it was a force speeding him up, speeding him up, speeding him up. And in fact, the next split second, he'll start having a force slowing him down as he tries to climb up. So what you realize is the very maximum of velocity happens as the kid gets to the very bottom of the swing set. And therefore, at that point, all of the energy is kinetic energy. So you can say it's also equal to 1/2 m v max squared, and V max, of course, is omega times A. So those are two ways you can look at the energy equation. Now, what I want you to realize is both of these allow you to get rid of the 1/2 like that, and you can then solve for instance, velocity. So if you wanted velocity, you could say velocity is equal to plus or minus the square root. So I'm going to take that top equation and solve for v. So the very first e equals k plus u equals 1/2 mv squared. I'm solving that one for v. What I'm going to have to do is divide through by k. That's going to give me k over m times a squared. So k over m times a squared. That's for the term that's on the other side of the equals. And then I'm going to have to pull the 1/2 kx squared to the other side. That's going to be negative k over m x squared, which I think you can see is in fact plus or minus, and we can't really determine the plus or minus, as you'll see in a later example, which one it actually is, unless they give you some more details. But basically what we're going to get is this k over m, which is common to both terms, times a squared minus x squared, and that's your velocity as a function of position. So if you had a position x, you could plug that in that x, and knowing a, you could find out what the velocity is at any point in time later. You could also go a little further, and you'd say plus or minus the square root k over m times, let's say, a squared. And then if you factor all that out, then you get 1 minus x over a. Both of those quantities would be squared like that, and the square root there. Now, in this case, it becomes v plus or minus. Now, when you take the square root of k over m, you just get square root of k over m, which is omega. And when you take the square root of a squared, you just get a. And then you're left with 1 minus x squared over a squared. And actually, I shouldn't have put parentheses around that. So let me put my square root here. And now it's going to be 1 minus x squared over a squared. Now, finally, one last thing. You can see that this quantity right here is omega. And omega times a, we just finished showing, was v max. So finally, we can say v is equal to plus or minus v max times the square root of 1 minus x squared over a squared. So that's a kind of helpful result. But we might also want it in terms of a, in which case we can just stick to what we had before and say that v is equal to plus or minus. And in this case, when we're doing it, actually, let me double check. I want to make sure I'm putting it in the same form that your book did. That was the Vmax form. I did get that. So I can say v equals plus or minus the square root of k over m times a squared minus x squared. Now, in principle, you could also solve for x the same way. Instead of having v on the left, you could actually solve for x, and that would give you the x for any a, if you know what the v max is. But we find that that's not that helpful, so we just don't use it. So let's look now at a very specific example of an energy calculation. So this is very much like your book example, where your book example is 1410. I'm doing more or less the same type of example, but I've made entirely different numbers. And actually the whole wording, everything's a little different basically. So a spring stretches by 0.200 meters when a mass of 0.350 kilograms is suspended from it. The spring is then mounted horizontally on a frictionless surface and the 0.350 kilogram is still attached. Then the mass is pulled to 0.150 meters from equilibrium and released. So the fact that it's released tells you that, for one thing, the amplitude is 0.150 meters, and for another thing, the velocity at t equals 0 is 0. So that's two important pieces of information that we got from there. So A says, what is the total energy? B, determine the kinetic energy as a function of time, and and U of t, the potential energy as a function of time. C, what is the mass's velocity when x is equal to 0.0750 meters? And then D, what are k and u when x is equal to a over 2? So let's attempt to solve this. So our solution, for starters, everything we know, whether I'm using energy or not, needs to have a k. So what we have is, at least in magnitude, F is equal to the magnitude of k times x. Of k times x. So what this gives us is 0.350 kilograms times 9.80 meters per second every second is equal to k times, when we hanged it on it, it was 0.200 meters. So from that, we can derive or reach the conclusion that k is going to be 0.35 times 9.8. Now I'm going to divide that by 0.2, and that's going to give me 17.15. And clearly that's one extra sig fig than we're really justified in using, so I'll underline it, and that comes out in newtons per meter. We can go a little further and say omega is equal to the square root of k over m, which equals the square root of 17.15 newtons per meter over, now we've got to put the mass, which is 0.350 kilograms. And now if I take that and divide it by 0.35, and then I take the square root, I get the square root of 49. And that is in radians squared per second squared. Technically, the radians I just threw in there. And obviously, this gives us omega is equal to 7.000 with one extra sig fig radians per second. Okay, so that's some of the information we need. Some other information we might want to know is, for instance, what is Vmax? Well, Vmax, we know, is omega times A. So we can say that's going to be 7.000 radians per second. And our A, as we said, was then the mass is pulled to 0.150 meters from equilibrium and released. So that's the A, 0.150 meters times 7. That'd be 0.7, and then that'd be 1.35, 0.15. 0.15 times 7. I think it's 1.05. 0.15, yep, times 7, yep. So this is equal to 1.05, and the next digit's actually 0, even though it's not a sig fig, so that's meters per second. So we've got all that information, and that's just stuff to help us based on what we just learned. So for part A, what they're asking for is, what is the total energy? So A, E is equal to K plus U, but we know it's also just 1/2 KA squared. I could have also used 1/2 M Vmax squared. That would have been fine as well, but I'm going to use KA squared. So I'm going to say E is equal to 1/2 times 17.15 newtons per meter times 0.150 meters squared. So I'm going to say 0.5 times 17.15 times 0.15 squared. And that gives me 0.1929. And the unit is joules, and I carried one extra sig fig. So that's the answer for part A. Anybody have any questions for that, about that? Okay, let me turn my chat on too. I noticed I did this the other day and forgot to ever put chat up, and people were talking to me, telling me that they couldn't hear me, and I didn't know a darn thing. I literally went through the whole class without hearing from a single one of them. I was like, I don't know why they're not so interactive today. Turns out I'm an idiot. That's why. So, all right, now that we got that, this is weird. Okay, I see. One of my little windows for Zoom just popped up in the middle of my screen. I didn't know why. So that is A, the total energy. B, what we want to determine is kinetic energy as a function of time and the potential energy as a function of time. So B, oops. Dang it. Stop that. Stop it. Okay. K of T is 1/2 K times X of T squared. Now, we know that's 1/2 times 17.15, again, newtons per meter with it one extra sig fig. And we also know X of T is, in fact, A cosine omega T plus phi. So I'm going to say A squared cosine squared. We already figured out that omega is 7.0, so 7.000 radians per second times t, like that. And in fact, because it was released, we know that A is equal to 0.15. Actually, I shouldn't try to fit that in there. That's a really bad thing I did. So I'm going to undo it, sort of. And I'm going to say like this and say that A is equal to 0.150 meters and phi is equal to 0. You can verify that yourself, but basically what you see is V of 0 equals 0 gives you 0 equals omega A times the sine of omega T, and or omega T plus phi. And the omega T for T equals 0 is just 0. So you get 0 equals omega times A, or actually negative omega times A times the sine of phi, and that only works with phi equals 0 or phi equals 2 pi or phi equals pi, stuff like that. We choose the simplest answer. Oops. So anybody have any questions on how it, dang it, on how I decided to do this? So I can go ahead and put this in. I'm going to say K of T, and of course I need to go ahead and write out what A is, but I'm going to do 0.5 times 17.15 times, now I'm going to do A squared, which is 0.150, so 0.15, and now I'm going to square that, and that gives me, lo and behold, something that looks very familiar, 0.1929 joules. That's the entire multiplier in front of the cosine squared. So the other part's just going to be cosine squared of 7.000 radians per second times t. Anybody have any questions on that one? So here's the other part. We need U of t. Actually, dang it, I just did U of t, and I've been calling it K of t all this time. I suspect y'all all know that was U of t. Did y'all recognize that? And I was just being a goober and didn't even pay attention to it. Go ahead and make your changes in your notes. Yeah, because that was, yeah. I don't know why I did. I guess because maybe I did it earlier today with I did the U first and just thought I was doing the K first this time. I don't know. Either way, it's just a dummy mistake by me, so I shouldn't have done it. I apologize. So what I'm going to say now is this is U of t. Sorry about that. Hopefully that makes sense to everyone. Did everybody get that? Anybody get confused by that? Anybody needs help understanding why that's okay? All right. So K of t, which is what we also are supposed to have, that's 1/2 mv squared. Now, x of t, we already determined was a cosine omega t plus phi, but that's all before the initial conditions. So I'll say before initial conditions. Okay. So what we're going to do is you see x of 0 is equal to 0.150 meters is equal to a times cosine of 0 plus phi. Doesn't necessarily allow us to determine phi, but if phi was 0, that would certainly be acceptable. So I'd say implies phi equals 0 is good, but not necessarily right, because you could also have phi equal to 2 pi or negative 2 pi and so on and so forth. But the other part is v of t. This is what I was just saying in words. So I realized how much I was saying in words, and I decided that maybe I should go ahead and carry out the derivation to show you. So v of t is equal to dx over dt. And when I take the derivative of x of t, I get the derivative of cosine is negative sine. So it's going to become, and I am using red, it's going to become negative omega a sine of, and that would normally be omega t plus phi, but we're sort of in that point where I have thought about phi being 0, but in this case, this will actually settle it for us. What we do know is that v of 0 is equal to 0.0 meters per second. That's equal to negative omega a times the sine of 0 plus phi. Now, if we made the omega 0, that wouldn't be very useful because we're getting rid of some of the fundamental aspects of the differential equation. And if we made the a 0, we're just saying the thing's not oscillating at all. So that's not very useful. So now we conclude phi equals 0. Okay. So that's what I was talking about. That's how I know the sine is 0. So now I can take and calculate K of t is equal to 1/2 times the mass, which is 0.350 kilograms, times, now we've got to square the velocity. So that's omega squared. Notice the negative is just going to become positive. So that's omega squared times a squared times the sine squared of just omega t, which means we can put all these values in. We get 1/2 of 0.350 kilograms times 7.000 radians per second squared times 0.150 meters squared times the sine squared of omega t. So I'll put an X here just to remind us that that's still multiplied. So I think you can probably figure out what that leading coefficient is going to be, but 0.5 times 0.35 times 7 squared times 0.15 squared gives me, lo and behold, 0.1929, carrying one extra sig fig again, joules times sine squared of, did I write it that way last time? Oh, I left off the omega last time. So I'll write it this way too, omega t, like that. So that's my K of t. So this is part B, and this is part B. Now you could also include it as equaling 0.1929 joules sine squared of 7.000 radians per second times t if you wanted, and that would be fine. So anybody have any questions on that part? Y'all can still hear me, right?
Yes.
Okay, cool. All right. So we've got part B. Part C, they're asking us to determine what's the mass's velocity when x is equal to 0.0750. Now, if we look, we actually computed that already. We know v is equal to plus or minus v max times the square root of 1 minus x squared over a squared. So I'm going to use that one. Of course, I could use the other one too. Doesn't really matter too much. But for part C, what I'm going to do is I am going to say that v is equal to plus or minus v max times the square root of, I think that was the one that was 1 minus, yeah. So that's 1 minus x, and I can actually put it like this and square the whole thing, which makes it a little easier to write. So I'm going to say it's plus or minus, we already calculated v max. I'll remind you because I wrote it right here. So I'm going to say this is 1.050 meters per second times the square root of 1 minus, now in this case, we're saying x, which is 0.0750, over the actual amplitude, which we decided was 0.150 meters, and then that entire quantity has to be squared. So if you take the 0.0750, oops, 0.075 divided by 0.15, I think y'all know what that's going to be. It gives you 1/2, and then you square it, that becomes 1/4, and then you do 4/4 minus 1/4 is 3/4. So you get 1 minus 0.25 is 0.75. I take the square root of that, and that gives me root 3 over 2, which is 0.8660. So this quantity is 0.8660, and then I'm going to multiply that by 1.050, and that gives me 0.909, and carrying one extra sig fig gives me a 3, and that's meters per second, and technically it's plus or minus because we really don't know enough information to say whether it's going to the left or to the right. So that's part C. Anybody have any questions on that part? Okay, so that's use of one of those velocity equations I solved for earlier analytically. So now you've seen how you can use that. Of course, you could have used the other one as well. And there was some advantage to using the other one because V was like a second or third calculation, whereas K was like one calculation. So if I would have used the K and the M and the A, I would have used a lot fewer variables that I had to calculate during the problem. So it would be less chance of making an error. But I'm going to continue now. So let's say example 14-10 continued. We're now going to do part D. And part D asked us specifically, what are K and U when X is equal to A over 2? So D, K equals question mark and U equals question mark when X is equal to A over 2. So that's what we're shooting for here. Now, the cool thing is this is really, really helpful because K is just equal to 1/2 M V squared. And we know V is equal to plus or minus V max times the square root of 1 minus X over A quantity squared, which we can say is plus or minus 1.050 meters per second times the square root of 1 minus, now X is supposed to be A over 2, so if you divide A over 2 by A, you just get 1 over 2, so you just get 1 minus 1/4 like that, which I think you see is exactly the velocity that we just calculated, which is 0.9093. Okay, so K is equal to 1/2 times 0.350, if I remember correctly. Yes, 350 kilograms times 0.9093. And that's meters per second squared. So I'll do 0.5 times 0.35 times 0.9093 squared. And that gives me 0.1447. And the 7's an extra digit, and that's joules. So this is part of answer D. Now, you know the total energy was 0.1929, so we could just do 0.1929 minus this, and that would give us the remaining energy, so that's acceptable. So, or you could actually calculate it, and U is equal to 1/2 K times X squared. So if we did that, it'd be 1/2 times 17.15 newtons per meter times, now we're going to take A over 2, which is 0.0750 meters, and we're going to square that. 0.5 times 17.15 times 0.075 squared, and that gives me 0.0482, and the extra sig fig is 3 joules, like that. So that should be the right answer for D. But like I said, we could have also said U is equal to, I'll call this alternate. We could have said U is equal to 0.1929 joules minus 0.1447 joules. So 0.1929 minus 0.1447, and that gives me 0.0482 joules. So that's a check that we've confirmed. In fact, it is the same whichever way we did it. Of course, that only brings us to 0 at the last real decimal place. Remember, the 3 was a non-significant digit. So, any questions on that one? Okay, your book actually asks a nice question. It says, this is conceptual example 14. Let me just write that. So conceptual example. Basically what they're saying is, if A changed to twice A, they want to know A, what happens to E total, B, what happens to V max, and C, what happens to A max. Okay. Now I didn't talk about A max at least this time, but hopefully y'all remember from last time. Anybody have an idea what the answer is for part A? Anyone? Okay, so remember when we first showed you the energy, what we found was the total energy was 1/2 Ka squared. If I switch from A being say 0.1 to A being 0.2, then what you see is the original energy was 1/2 K times 0.1 squared, but the new energy is 1/2 K times 0.2 squared, which you can also write as 0.1 squared times 2 squared. So you see that the energy total E total goes to twice E total, or excuse me, 4 times E total. Because E total equals 1/2 K A squared. E total 1 was equal to 1/2, let's say K times A squared, and E total 2 is equal to 1/2 K times 2A squared, which is equal to 1/2 K A squared times 4. So if you divided E total by 2 by E total 1, you'd get 4. So that's what happens to the energy as far as part A is gone. So anybody have any questions on that? Now, the other thing you need to realize, and I've already sort of given you a hint on this, basically V of t is dx over dt, which is negative omega A times sine squared, or excuse me, times the sine of omega t plus 5 for any arbitrary problem. And you see that this is V max. So V max is proportional to A. Therefore, V max goes to twice V max. Does that make sense to you folks? Everybody follow why I did that? How that works? Now the other part is part C, and A is equal to dv dt, which you can tell is going to be negative omega squared A cosine omega t plus phi for any arbitrary problem. And you see that this is A max, and A max is proportional to A again. So this tells us that A max goes to 2A max. And that's the answer to part C. Any questions on that? Nothing? All right, so that's the energy considerations. Now, what I want you to understand is how do we deal with this new idea of a simple harmonic oscillator behaving some way? Your book takes some time in 14.4 to tie together the sinusoidal or simple harmonic motion that we had by tying it to a model where you imagine there's an object just going in a circle. So there's an object going in a circle, and you want that object in a circle to be somehow related to x equals a times cosine omega t plus phi. Well, if you think about it, if you make the circle have a radius of a, then when the thing going around the circle, and we'll say the circle's centered on the origin, when the thing is going around the circle, once it gets on the x-axis, since the circle has a radius a, it'll be at positive a, and then as it spins around and hits the y-axis, it'll have x equals 0, which is like the equilibrium position. And then when it hits the far side, it'll be at x equals negative a. So that sort of looks like it. And in fact, if you try to do that, you'll find that as long as you keep that as your model, you're going to say, okay, well, there exists a model in which something is rotating with an angular speed omega in a circle of radius a. And that faithfully represents, when you just look at its x component, that faithfully represents the simple harmonic motion, which just oscillates back and forth in A, and it justifies us using the omega. Because remember, omega is supposed to be the instantaneous rate of change of the theta with respect to time. But if you're talking about something oscillating back and forth, then that doesn't make very much sense. There's no theta on a spring with a mass, right? So the omega turns out to be just 2 pi times the frequency, where frequency is understood to be a quantity that basically says a certain number of cycles is completed in a given number of seconds. So yes, omega is related by multiplying that by 2 pi, but you can see there's actually a omega that is rotating that can be directly tied to it, and it's the model of a circle, basically an object going around in a circle of radius a, with its center at the center of the xy axis, and the simple harmonic motion is just what the x coordinate's doing. So anyways, that's what your book talks about in section 14.4. It's kind of nice. It just gets the mathematics right. But what I want to do now is talk about a simple pendulum. So if we imagine a simple pendulum, what we'd say is a simple pendulum is basically a ceiling. And what we're going to do is we're going to imagine that there is a vertical line here. We're going to stretch out the string whose length is L. We're going to stretch that out to an angle theta. And in fact, what's going to happen is this distance right here is actually L times theta. What we see, though, is there is a force acting straight downward. If this is an object of mass m, for instance, this force is m times g. And of course, you can use your ideas about geometry to say that this line continues, so this angle will be theta, and then you get this vector and this vector. This one would be mg cosine theta, and this one would be mg sine theta. Now, the mg cosine theta is just being canceled out by, let's say, the tension in the string. Oh, I drew that kind of crooked. But that's the tension in the string. So the mg cosine theta, let's say t minus mg cosine theta is equal to 0. And what we're left with Newton's second law is the summation forces is equal to mass times acceleration. And this case ends up giving us m times g times the sine of theta with a negative is equal to m d2s over dt squared, where s is that little arc length that I drew in there. Okay. That is not a simple harmonic oscillator. For instance, if I divide both sides by m, you end up getting d2s over dt squared plus g sine theta is equal to 0. So that has almost no resemblance to the simple harmonic oscillator. But if you do a Maclaurin expansion of sine theta, you'll find that sine theta is an odds function specifically because the first term is theta to the 1. The second term is theta cubed over 3 factorial. The third term is positive theta to the 5th over 5 factorial, and then so on and so forth. But for small angle, sine theta is approximately equal to tangent theta is approximately equal to theta, and that's what we're going to use. So if I say d2s over dt squared plus g times theta is equal to 0, I'm almost there, but that theta is not that helpful for me. What I'm going to do is realize that s is equal to L times theta, so that this becomes L times d2 theta over dt squared plus g times theta is equal to 0. Divide through by L, and I get d2 theta over dt squared plus g over L times theta is equal to 0. Now we have the simple harmonic oscillator equation. This has a solution, theta equals theta 0, say, or you could say A if you wanted to. The main thing is the next part is cosine omega t plus phi. And I think you can tell from here that omega will be equal to the square root of g over L. So that's the key to actually applying this simple harmonic oscillator understanding to general problems. Now, what did I actually do? Well, you could actually put in this solution theta equals theta 0 cosine omega t, and what you get is theta dot is equal to negative omega theta 0 sine omega t plus phi. And then you could say theta double dot. Again, these dots are Newton's representation of derivatives with respect to time. So when I say theta dot, I mean d theta dt. And when I say theta double dot, I mean d2 theta over dt squared. When I take this, I get negative omega squared theta 0 cosine omega t plus phi, like that. Okay. Now, if I plug all that back into the equation, I get negative omega squared theta 0 cosine omega t plus phi plus G over L times theta 0 cosine omega t plus phi is equal to 0, but this has to be true for all time. So when we separate this out, we can see that negative omega squared plus G over L times theta 0 cosine omega t plus phi is equal to 0, and that can only be true if omega equals the square root of G over L. So that's the little step you've got to remember when you go to apply this to a particular problem. Just because it looks like a differential equation that is a simple harmonic oscillator, you still got to figure out what omega is in that context, and that's the way we do it. Any questions on that? Your book does take the time to show you that in that small angle approximation, there's a table 14.1. I'll just say C table 14-1, and what you see is theta equals 30 degrees, which is also equal to, of course, 0. Whoa, is also equal to 0.52360 radians, implies sine theta is equal to 0.5. Dang it. .5, whereas theta is equal to 0.52360. So you can see that there is a difference, but the difference is only about 4.5% difference. So even up to 30 degrees, you only get about 4.5%. So the small angle approximation is really not a problem. I also gave you a little bit more by telling you that we use sine theta is approximately equal to tangent theta, but it's also approximately equal to theta. So if you actually look at the Maclaurin series expansion of tangent, you'd find that the first term is also just that theta. So hopefully that makes some sense to you. As an example, let's look at example 14.2. So not 14.2, 14.12. Example 14-12. Basically, a geologist finds that a 37.10 centimeter pendulum has a frequency equal to 0.8190 hertz. What is G? So that's the question. Now, what we know here is omega, which is 2 pi f, is the square root of G over L. If you ever forget whether it's the G on top or the L on top, remember omega has units of radians per second, so it needs a second in the denominator. And the only thing under that square root that has seconds is the G, and they're in the denominator, so the G must be on the top. Hopefully that'll help you. But if I square both sides, then I can get 4 pi squared f squared is equal to G over L. So we get G is just equal to 4 times pi squared times L times f squared. So that's 4 times pi squared times 0.3710. So notice I did convert it to meters. Times 0.8190 hertz squared, And when I do this math, I'm going to say 4 times 3.14159 squared times 0.3710 times 0.8190 squared. And that gives me 9.8243. That's one extra sig fig, and that's in meters per second every second. And that is actually a good way of determining gravitational acceleration anywhere you go. If you have a really precise way of measuring a period of a pendulum and a very precise measurement of the length of the pendulum arm, then you can determine G pretty accurately anywhere on the planet. Of course, it would help to not have too much air resistance and stuff like that, but you'd be surprised how little that matters over a 1 or 2 or even 10 cycle period. Anybody have any questions on that? Okay, so the physical pendulum is another scenario we should be able to understand. Again, in this case, it's going to turn into a simple harmonic oscillator, but I want to make sure you can do that one as well. So with the simple pendulum, you're going to imagine, again, a ceiling or something from which it hangs, basically. So I'll put a little hook right here, say. And actually, a hook's probably not the best thing. Let's get rid of that. Let's say I have a rod with a nail sticking out of it. Ooh, really fancy. Okay. So now my object is in fact going to be like a baseball bat. And the baseball bat is going to go like this and get wider. And now it's become a softball bat. And that's okay. Okay. So what we're going to do is imagine, again, this is a vertical. Let's say this line is the symmetry axis of the bat. And of course, right here, we might say is the center of mass of the bat. And what we learned in chapters, 1 through 10, basically, was that when forces act on a body, we can pretend like that body is a point particle, and then all the forces act right at the center of mass. But then if you want to figure out, well, how does the body twist and turn over time, then you have to talk about torques and stuff of that sort. And, about what angle is it, about what point is it rotating or oscillating, stuff like that. So we're going to have to bring that back as well. But in this case, there's your angle theta. Let's say this quantity from here to here is a quantity h. That's how far the end is from the center of mass. And what we can do is realize that we're going to have a vector mg pointing downward. We can break that vector up because, again, this angle will also be theta. And we can break that up into a vector that acts right through the center of rotation. That is mg cosine theta. And then there's another force that acts, and that'd be mg sine theta. But notice that one acts perpendicular to the lever arm. Okay, so we can, in this case, we can use the summation of the torques is equal to I times alpha. And what we're going to have is this torque tends to correct again. So we'll say this is negative mg times h. There's your lever arm, times the sine of theta. There's us finding the component of force perpendicular to the lever arm. That's all equal to I, the moment of inertia of the thing about its end, times d2 theta over dt squared. Okay. I can write this in an attempt to make it into a simple harmonic oscillator I can write it all on one side and get the leading coefficient to be 1, in which case this side's going to be m times g times h over I, and I can use the small angle approximation, which is theta. So I'm going to say for small theta, sine theta is approximately equal to theta. So now you can see we do in fact have the simple harmonic oscillator, and what we're going to say is theta is equal to theta 0 times cosine omega t plus phi, where omega is equal to the square root of m times g times h over I. So see how you do that? We just knew it's going to be a square root of whatever's in front of the term that has the 0th order derivative. Or like I said, you can throw this theta equals theta 0 times cosine omega t in there and get your characteristic equation like I did before. And that works well as that works good as well. Any questions on that? All right, well, your book does a really good example with this type of problem, and it's going to be example 14-13. So it says, suppose an irregularly shaped object can be balanced at a point, let's say 39.0 centimeters from one end, and its mass is, let's say, 1.50 kilograms. If it oscillates from, I shouldn't say from that end, that's very, if it oscillates with a period of 1.80 seconds when suspended from that end, what is its I about that end? That's part A. And part B, what is I about its center of mass for a parallel axis? Okay. So we have a problem again. What we know is omega is equal to 2 pi times f is equal to the square root of mgh over I. And we also know f is equal to 1 over t. It looks like I'm going to write the solution in the same color as I did before, and that's just fine. So I'm going to say 2 pi over t is equal to the square root of mgh over I are 4 pi squared t squared is equal to mgh over I. Finally, what I'm going to say is I is equal to mgh over 4 pi squared. And then all of this will be times t squared. So I think that works. Anybody see any problems with that algebra? All right, so let's calculate I. This is for part A. I is equal to 1.50 kilograms times G, which is 9.80 meters per second, times H, which is 0.390 meters. Notice I did have to convert it to meters. And then all that will be divided by 4 times pi squared, and then times the period, which is 1.80 seconds squared. So when I do all this math, I get 1.5 times 9.8 times 0.390 times 1.8 squared. And then I'm going to divide by parentheses 4 times 3.14159 squared, close parentheses. And that gives me 0.4705. And because it's a 5, I need to put the next digit. So that's extra units there, but that's kilograms meters squared. So I about the end is equal to 0.47050 kilograms meters squared for that. Now, part B, they want to know what is the center of mass about this, what is the moment of inertia about the center of mass using an axis parallel to that other one. So the parallel axis theorem tells us that I is equal to I center of mass plus m d squared, where d is the distance from the axis to the center of mass. So for this one, we're going to say ICM is actually equal to I about the end, which is the one we just calculated, minus 1.50 kilograms times 0.390 meters squared. So I about the center of mass, I'm having a hard time drawing center of mass or CM today without making it crazy. Okay, so ICM will equal 0.47050 kilograms times meters squared minus, minus 1.50 kilograms times 0.390 meters squared. And this gives me 0.2424 kilograms meters squared. Anybody have any questions on that one? All right, so we got a little bit of time left. You can look, your book does a torsion pendulum. That's sort of the same thing, only they even spell out how for you how you're going to go about getting omega. So I'm not going to spend any time with that. We already told you about the damped harmonic oscillator. So you know basically the damped harmonic oscillator has a equation of motion, which is another word for Newton's second law, of the summation of forces is equal to m d2x over dt squared. So in this case, what we're going to say is m d2x over dt squared is equal to negative kx, because that's Hooke's law. But then in addition to that, we're going to get negative b times v. So that's actually damped by air resistance. Air resistance can either be proportional to v or proportional to v squared. We're actually handling the proportional to v story. When I reconfigure that, what I end up getting is d2x over dt squared. So notice I divided through by m, and plus b over m times v, which, by the way, v is dx dt, plus k over m times x is equal to 0. That's the equation for damped simple harmonic oscillations. So it's sort of a misnomer to say damp simple, but you get the point. I'm just trying to say that's what it is. And the solution for that is x of t is equal to a e to the negative gamma t times cosine omega t. And in principle, you could continue to go with omega t plus 5, but your book's choosing not to do that. And they're going to call the omega prime instead of just plain omega. So that's what their solution is. You can take the derivative of that and then take the second derivative of that and then plug all that in, and you'll see exactly where the gamma comes from. But generally speaking, we say where gamma is equal to b over 2m and omega prime is equal to the square root of k over m minus b squared over 4m squared. Notice that's b over 2m squared is what's in there. But that's basically the solution. So whenever you see a differential equation that has a second order derivative plus a number times the first order derivative plus a number times the 0th order derivative is equal to 0, then you know it's a damped harmonic oscillator. So actually, let me go ahead. I don't like that I called it that, but it's a damped harmonic oscillator. Okay. Now you can see other problems that look like it that might not look that much like it, like your book does an example 1414 for a pendulum with damping. So see example 1414. In that case, you have to figure out how the pendulum changes gamma and omega prime. So to do that is another instance where you've got to take the time and write out the differential equation. Again, what they're going to say with the pendulum is you're going to have a b times a dx over dt. That dx over dt is really going to be a ds over dt, and that s is going to be L times theta. So you can just get L to be the length of the pendulum, so on and so forth. But in doing so, you can then figure out what that is and solve that simple problem, if you will. So that's really about all there is. Your book does take time to show you that a e to the negative gamma t cosine omega prime t is a solution. That's a worthwhile thing for you to do just to get better practice with your derivatives. It also then talks about forced oscillations, and they really don't give you any actual examples to work out other than problems at the end of the chapter. So I won't be questioning you on that as well. It even talks about the Q value. I will not be testing you on that. So you're not required to know that stuff. There may appear questions, because I think it's worthwhile for you to do homework wise. There may appear one question, say, in the homework, or maybe a couple questions in the practice test. So don't freak out if you see those. Just know they will not be on the test. And in fact, if you take the test and find there's a question like that, let me know, and I'm going to have to give you the points. So now, with that being said, we're now 2 minutes shy of class time being over. We have completed chapter 14. Next time, I'm going to do a lightning round of chapter 5, because there's really only a few things that matter that much to me in chapter 15. I think I said 5 just now. I don't know why, but it's only a few things that matter. So we can knock that out really quickly on Wednesday. And then, of course, Monday, since your lab meets on Monday will be your final exam. I got my students to show up like, well, actually, no, it's during your lab, so you're golden. Never mind with that. I had one class that didn't meet their lab on Monday, but you guys meet your lab on Monday, so you should be able to do that. As far as I can tell, you'll still have your normal lab instructor. I'll make sure she can do it. If not, it might be me doing it. But the main thing is it's going to be a face-to-face in the lab setting, taking the exam. If you have a computer or a tablet that you can use, as long as it can access TCC's Wi-Fi, can run Canvas, can run Canvas tests, can run Respondus Lockdown Browser and Respondus Monitor, which I don't think we're going to have to use Monitor. As long as it can do all that, you're free to bring it, and it would help us if you do bring it, just in case we don't have enough computers, but I don't think that's going to be a problem. Now, one last thing, we got 1 minute left. I want to let you know that if you look in your modules, I did open up a test 8 practice test. So you have a test that'll be due Sunday before your final, but it's completely helpful for your final because you're doing chapters 11, 14, and 15. So you'll see practice test 8, chapters 11, 14, and 15 is now available in your practice tests. And I'm also going to go ahead probably tonight or tomorrow and make test 8 available. But like I said, you have until 11:59 p.m. on Sunday to get that done. And that just counts as another one of your online tests. I think it'll help you nicely. And sometime tonight or tomorrow, you will see a practice final up as well. So you guys are free to go. I'm going to wait for the last person to leave in case anybody has any questions, but thank you for coming, everybody.
I do have a question, and it concerns the homework.
Okay.
Here we're talking about chapters 14 and 15, and I don't have it in front of me right now, but I could have swore homework's went up to chapter 35, 37, stuff like that after 15.
Right.
Are we still going to be responsible for that?
No. So I think I sent an email about that. Basically, what you're responsible for is chapters 1 through 11, and then 14 and 15. Anything you do outside of that is going to be purely extra credit to help your grade.
Yeah. Okay.
So even if they aren't marked with extra credit, so it's just 1 through 11, and then 14 and 15. That's all you're required to do. Everything else is just icing.
All right. Perfect. Thank you.
No problem. You're welcome. Anyone else? Brandon, Alyssa, John, Josh? Actually, that was John I was just talking to.
Hi, Professor. Yes, I have a question.
Yeah, I did get your, you sent me a text message about taking the test early, right? Oh, no, that
no.
was Angelica. No, sorry about that. Another A name. Go ahead, Alyssa. Sorry about that.
It's okay.
Welcome to old hood.
The one test that you had extended it, I think it said the 22nd. I think it was chapter 6, 7.
Yeah, it's test
online.
6 on chapter 7 and 8. Yeah, that's November 22nd. Did you miss that?
Yes, I did miss that test, and I was like mistaken. I don't know why. I thought I heard you say another date, and I did not go back and check. So
well, that's okay. I've screwed up a lot, so I'm going to give you. Not only am I going to give you another chance, I'm going to give you another chance with the practice test too, because I don't want you taking that and not being up to speed on it. So I'm including Miss Oliphant.
Thank you so much.
You're welcome.
I did the same thing. Thanksgiving was a little busy for me.
Okay.
I forgot completely.
Can I
Lots
make
of
it due
travel.
on the 30th for both of y'all?
That
Yes,
sounds
that's fine.
extremely yeah.
Okay,
Thank
cool. I'll put it on the 30th at 11:59. That's Thursday of this week, and I'll include. What's your last name? Is this Brandon?
you. Josh.
Oh,
Curry.
Josh. And it's Josh Curry.
Yes.
Gotcha. Okay, so you're in there too now. So I've got. Oops, wrong name. Or actually, I put you in the wrong slot. So Josh, you're both in there. Anybody else in here needs that? I don't think there is, but just in case. So I've got November 30th, 11:59 p.m. And that's the due date as well. I just made the practice test available till then. Now I'm getting ready to do the same thing for the actual test. Okay, so y'all can still take your practice test, and then once you feel like you're up to it, but before Thursday at 11:59 p.m., you can go ahead and take the test.
Thank you.
You're welcome. Good luck. I hope y'all do well. Anybody else have any questions?
Thank you, Professor.
You're welcome, Melissa.
I had a quick question about the lab final.
Yes. What can I help you with?
So
So
I
I don't
believe
know
our lab
anything about it, but your instructor will. But go ahead.
Oh, okay. I thought our lab instructor thought that it was going to be like on lockdown, but not in the classroom.
Okay.
So are you saying our actual in-class finals in the lab classroom? Because she made it seem like that was the last time we were meeting.
That's what I was planning. If that's the fact, then I might actually just make it the other way around, or I make y'all come in or whatever. But I think in light of her believing that, then I'll probably just make it online. So you will have to use your Respondus lockdown browser. So I will send out an email about that. That's on me, not on you. Okay.
Okay, and then I also had a question about the practice tests. Are those I know they're graded on Canvas, but are those like official grades, like something that actually plugs into our final grade, or is that just like
it helps you in that basically I take for each practice test we have, I take the highest score you get on each one and I average those. And then I take that average and divide it by 20, and that many points is added to your course grade. So it's like
it's
up
like
to
extra
5
credit?
points on your final grade. Yeah.
Oh, nice. Okay, cool. Because I forgot to take like the very first practice test, so I wasn't sure if that was gonna like negatively affect me or anything, but that works.
It might be a difference between you getting 4 points on your final grade instead of 5. So it shouldn't matter that much, really, to be honest with you. And I doubt
Okay.
it's even going to be 4 points because we got like 8 practice tests or 9 practice tests. So each one's only worth like 11%.
Okay, cool. I appreciate it.
You're welcome. Have a good one.
You too.
Bye-bye. It looks like that's it. So thanks for coming, everyone. Bye-bye.